We present a sampling-based approach to static correlation visualization for time-varying volume data. Shown here is a climate simulation dataset provided by the National Oceanic and Atmospheric Administration. Here we study two variables, temperature and salinity, and examine their correlations patterns. Let's first talk about how to compute the correlation. Given a specified reference location, the temperature time series at this location can be correlated with the temperature time series at all other locations. Each reference location has a corresponding 3D spatial correlation volume. Since the number of correlation volumes equals the number of voxels, it would be difficult for a user to exhaustively examine them to detect connections and infer the correlation pattern. Our goal is to provide a static view that captures the essence of correlation relationships in a cost-effective way. We present three sampling schemes to speed up the correlation computation and classification. First, we leverage domain knowledge to select important samples. Second, we compute selective sample pairs and interpolate the distance matrix. Third, we approximate volume-based correlation with sample-based correlation. In order to reduce computation time, it is necessary to select important samples for correlation calculation. In the first step, we incorporate climate scientists' knowledge into sample selection. As a result, the regions near the equator and sea surface have higher probabilities of being selected. This figure shows 2,000 selected samples. To build the distance matrix, both of the two axes must follow a 1D ordering of the selected 3D samples. We traverse the 3D samples using a Hilbert space-filling curve, which ensures that spatially close samples in the 3D data are likewise close in the resulting 1D ordering. For each pair of samples I and j, we compute their correlation volumes distance by considering the distortion of histogram distributions between the two correlation volumes. We apply Jensen-Shannon divergence to calculate the distance between correlation volumes and store the distance value in the distance matrix. The resulting matrix is symmetric. In practice, we compute selected sample pairs on a sampling basis, and the distance values for the rest of pairs are interpolated. Here we show the progressive computation of the distance matrix. With this sampling strategy, we sample more from regions of dissimilar pairs and less from regions of similar pairs. This visualization allows us to intuitively observe the iterative process and provides feedback as to when the sampling and calculation can be stopped. After computing the distance matrix, we use a hybrid k-means algorithm to classify the samples. The input to the k-means clustering is all samples, each containing a 1D vector of distance values with respect to all other samples. At runtime, the user picks the number of clusters, or our algorithm can automatically determine the optimal number of clusters. The output is the classification of all samples. In this example, we show static views of the salinity self-correlation and temperature and salinity cross-correlation for 20 and 100 years. A total of 5 clusters is generated. With the static view, we can easily tell the correspondence between different numbers of clusters. Notice that for correlation classification, the salinity self-correlation is more sensitive to the number of time steps chosen than the temperature and salinity cross-correlation. With the proposed sampling techniques, we can efficiently produce static visualization and keep the error within a reasonable range. In this example, we show timing and misclassification rate for salinity self-correlation computation with different numbers of samples. A good trade-off can be made between the number of samples selected and the misclassification rate. For the climate dataset, choosing 2,000 samples is reasonable, as we can compute within a few minutes while keeping the error small. In this example, we show the temperature self-correlation classification result. Note that samples A and B are drawn from the same cluster, their corresponding correlation volumes being similar. Samples C and D are drawn from different clusters, their corresponding correlation volumes being dissimilar. This static clustering result thus gives us a meaningful overview of correlation relations with respect to various sample locations. We believe that our sampling-based approach can be applied to other scientific fields where correlation study plays an important role in the analysis and discovery.